today. And David is going to be telling us about the expectation maximization method. And the sort of programming portion of this talk is just going to be integrated throughout. So you'll probably at some point be opening Python windows and doing work. So without further ado.
Okay, make sure that's right. Okay, so me again. So this is going to be quite different from this morning's lecture. So there we were really trying to get a very broad overview, build a mental map of the whole landscape of machine learning in astronomy. And here, by contrast, what we're going to do is a deep dive in one particular method, something called expectation maximization. You've already seen a little bit of it when you learned about Gaussian mixture models yesterday. So, and I know it's getting towards the end of the day, so I want to keep this moving. So instead of having kind of a big programming exercise at the end, I'm going to have small programming exercises that are mixed in. Okay, so you'll need to be opening your laptop. There's no IPython notebook provided because you're just going to open up a fresh one to do the exercises. And when we do the exercises, I'd like you to work again in pairs, so using the pair coding approach, which I think you're already familiar with. So, do we agree? Everyone's familiar with the pair coding? So what I mean by that is basically one person drives and the other person types. So, and then you'll switch from one exercise to the next. Okay, so why did I pick this one algorithm to do a deep dive on? So the reason is because I consider expectation maximization, because that's a mouthful, I'm just going to say EM from now on. I consider the EM algorithm to be really one of the miracles of numerical analysis. Okay, it doesn't have the fancy Bayesian credentials that everyone likes, although there is a proper Bayesian way to use it. But it really is kind of a classical numerical analysis. It's what I would consider a minor miracle. And what I mean by that is that it's remarkably fast and stable. It has good, provable, rigorous convergence properties. And whenever you come across with a miracle like that, you should always try and adapt your problem to take advantage of it. Okay? And another striking example, kind of a miracle in numerical analysis, is the fast Fourier transform. Okay? Whenever you can turn your problem into the fast Fourier transform, you always should. Okay? It's very fast, it's very stable, it has great numerical accuracy property, the FFT. So the main kind of the classic applications of EM that we're going to focus on are in unsupervised learning to discover clusters in your data. So that's the context that came up yesterday. But also in nonlinear regression. So if you want to perform a maximum likelihood fit to a model which is a mixture of different components, the method is very general, but almost always the way it's applied is to do to a mixture of Gaussians, and you'll see why that is later on. But if you didn't have this technique, what you would be doing if you're summing, if you have to do a maximum likelihood fit to a sum of Gaussians, the number of parameters blows up very quickly, and it's even doing like a fit to 2 or 3 Gaussians, say in 3 dimensions. The number of parameters, the maximum likelihood fit is very unstable. If you look at the surface, an optimizer, steep descent, things like that, they can't handle it at all. It'll take a long time, and they won't ever converge even to a local minimum. And by contrast, this algorithm, viewed as a maximum likelihood method, is extremely fast and stable. Okay, so the outline for today is I'm going to focus first on Gaussian mixture models, because that really sets the context. And then we're going to talk about another one of the kind of recurring themes in machine learning methods is something called latent variables. I don't know where that terminology came from. It sounds like thermodynamics, but it just means basically a hidden variable. It's a variable that you wish was in the data, but isn't actually there. And then we'll talk about expectation maximization. So that's the algorithm that we use to fit our data to a Gaussian mixture model, either for doing clustering, unsupervised learning, or because we actually want, because that's really a physical model and we want to get its parameters. And then I'll end up giving you some practical advice on how to do these things, and then show you some advanced applications of this, just to show you that this is really a solid foundation that you can build a lot of other useful tools on. Okay, so first of all, Gaussian mixture models. Okay, so the idea here is that we've got n-dimensional data. Okay, so a constant, n, capital N is to be constant, is the dimension that we're living in. And we want to model it as a sum of independent Gaussians. So we have k of those, capital K. Okay, so I've written out the probability. So given a particular data point, that's an n-dimensional vector, this is the probability. And this looks kind of like a mouthful here, and that's because I've tried to be explicit. Usually you'd see this written much more compactly. Sometimes people will put all of those parameters and just call it theta. Okay, but I mean that's nice and short to write, but you have to really think about what really are the parameters. So I've written them out here explicitly. And another complication is that we have kind of two dimensions to this problem. We have the number of spatial dimensions, n, and we have the number of mixtures, k. So I've used boldface for things that are live in the n-dimensional vector space of our data, so x does, and the mean of each Gaussian, that's also a vector in our n-dimensional space, but nothing else is boldface. These are just constants, they're coefficients. Okay, so we're going to take a sum of Gaussians, and so the alphas are just how much of each Gaussian you have. They're normalized, so there's really, although we have k of them, since they add up to 1, that's a constraint, so there's really only k minus 1 independent degrees of freedom. And then, so that coefficient multiplies just the normal Gaussian, also the multidimensional Gaussian. And then the last thing we haven't talked about is this covariance here. So we're considering the most general Gaussians here. So this is actually an n by n dimensional matrix. So it's got more parameters than the mu's, the means, but it's not n squared because of the symmetry of a covariance matrix. We'll see that explicitly in a minute. Okay, so that thing on the right, again, that's a pretty compact notation for something that's a little unwieldy. I find this is, there's a lot of classic distributions in statistics, Poisson, Gaussian, log normal, all those things. This is the only one that I use so often that I can basically write this down in my sleep in this form right here, because it's so useful to know it in the n-dimensional form. So I think this is probably this is the only one that I could really do cold. I would even have to think a little bit to write down a Poisson distribution, to be honest, to get all the factors right. Okay, but this is a good one here, but this is glossing over a lot of details. Like, what is this absolute value mean? I thought that was a matrix. Notice there's a little transpose there, and then here we have C, but here we have C inverse. So that's actually quite a lot of linear algebra that's hidden inside of that that expression. And then the covariance matrix. So it's almost always more convenient to think of the covariance matrix in terms of a different, instead of thinking of it just as Cij, think of it in terms of on the diagonal, the covariances are just the squares of the sigmas. So basically the RMS value for a given for one of the dimensions in our data space. And the off diagonals, they introduced us one extra parameter once you know the sigmas, so it's useful to write them in that way, because this thing here then is always going to be dimensionless, and even better than that, it's always going to be between -1 and +1. So that's what's called the correlation coefficient, and it's symmetric. Rho ij is equal to rho ji, which means that that's where the symmetry of the covariance matrix comes from. Okay, so we've got so here we've taken out the alphas because that's kind of an overall factor here, but we still got the mu's and the c's. Those are all the parameters that are hidden in here. Okay, so as a warm-up exercise, I want you to open your laptop, and I want you to write a NumPy expression that actually calculates that formula. Okay, so this is, you write a Gauss 2D, so it's going to take, we're just doing this in 2 dimensions, so we've got 2 components of our data vector, the 2 components of mu, and then instead of the 4 numbers for the covariance matrix, we've got sigma 1, sigma 2, and rho 1, 2. I'm going to go back to show you the expression in a minute. Okay, but just as a hint, so I want you to do this just using like fundamental NumPy operations. Okay. I mean, there is a SciPy function that will do this for you, but I mean, the point is to actually, in order to, by coding it up, you actually forces you to think about what this expression really involves. Okay, so this is pair coding here, so I want you to discuss. One person types, the other person.
Oh, sorry. I mean, so the question is, do we do this in a matrix?
Okay, so this lets you do
These are the NumPy functions that you're going to find useful here. No, not sorry, not.
How do we do the
Yeah, so we got a question here. So what is the absolute value of the covariance matrix mean there? That's nonsense, right? You can't the absolute value of the matrix. It's the determinant, yeah. So that's an example. There's a lot of detail in there. And you can calculate the determinant with this function here.
Create a Python function where you basically calculate.
Oh, so thankfully the order doesn't have to go.
It's going to flash back to this screen. So this is how you should declare your function, like that. Yeah, so if you just put into Google np.linalg, you'll see what that hint is about.
Why are you multiplying?
Oh, not it should be squared. But Cij is rho ij.
So
there's only one.
So this is what's
right. Oh. Oh, so okay.
If you have a question or you get stuck, just put up your hand.
Should I just do So there are two dot products.
which two vectors are you trying to dot product?
So I'm trying to take the dot product of this inverse vector with the matrix.
As soon as I start with the covariance.
With the covariance matrix.
Right, so this here is x minus 2.
Yes. Oh, maybe I.
So that's what you have to take the first one. So you have to subtract the two vectors.
Oh. T and then C.
So you want the inverse? Yeah, you might be able to just
Because it's not quite the transpose.
Correct. Yeah, here. Inverse. So lineage dot in.
Does anyone think they have an answer?
And then there's another dot product.
Close?
It was on the bottom right, yeah. You already have it as Oh, I see.
Alright, let's try.
You want to give it a list of values.
Oh, right. Sorry. I think it's. I still have to keep the practice.
I just wanted to be one.
Yeah.
It's probably easier if you just
I would try to use it as a second block to see what everybody's
Never not.
Okay, so I want to talk about this. So this is something that you have to do surprisingly often in your research. You'll read a paper, it's got this cool model for the dark matter density or whatever. It's an equation that's 3 lines long.
Hey guys, let's listen to David.
And you want to write a piece of code that you basically want to ingest that theory into your piece of code. And often it's a lot more complicated than this, and it's written in this compact mathematical notation. So the going from a mathematical expression, analytic expression, to code that really calculates the same thing is actually a trivial thing. And although it's more work, whenever I have to do this, always what I do is I'll first code it in Mathematica, and then I will code it in Python or C, whatever language I actually want it in, and then I will cross-check those against each other. Okay, if I really have to be able to trust the answer, I do the extra work to do it in Mathematica, which will where I know there's basically no numerical approximations. I trust that when I say integrate in Mathematica, it will integrate sufficient accuracy. And so, so here I provided, and if you didn't get this far, you can keep working on this later and to check this answer right here. Okay, and I'll just brief. Do you want me to show you the solution, or do you want to look at it later so you can work on it more? Put your hand up if you want to see the solution now. Okay.
First, can we see those numbers?
Well, let me. The numbers are in here. Okay, so this is the notebook that I'll put on the repo, and so I have the solutions to the exercises. So this is the solution that I did. So first of all, I built the covariance matrix like that, and then I calculated its inverse. Then I calculated the normalization factor, so that's where the determinant comes in, and then the 2 pi factor. And then I calculate the delta, so that's the x minus mu. And then I calculate the argument of the exponent, and then I finally just take the norm times x to the argument. So it's kind of like each line is pretty short. The nice thing about doing it this way is you can check each intermediate expression against Mathematica the same way. And then, of course, there is a SciPy function that does this already, so it already knows about a lot of the standard distributions. It's not going to know about the latest dark matter model, so this is still a useful skill to have. And then I check that they both give exactly the same answer. Okay, so keep your laptops up. And so now what I want you to do is I want you to solve. This is not the Gaussian mixture problem. It's a much simpler problem, but it helps motivate the Gaussian mixture problem. So what I've done is there's a file that's in the repository now. It's under day 2, and it's called tag-gmm.dat. It has 3 columns in it. So this is x1 and x2, so this is 2-dimensional data. But the first column is a tag. It tells you that this sample belongs to this Gaussian. And I plotted the data here. You don't need to make this plot. I'm providing it. So this is just color coding each of the samples that's in there. So what I want you to do is I want you to read this file in your notebook and now tell me what are the model parameters. Okay, so we have alphas, we have mu, and we have c's. There's 3 Gaussians, right? So there's 3 alphas, there's 3 means, there's 3 covariance matrices. Okay. So here's some hints. So first of all, it's always good to just make sure you understand what the question is. In particular, how many parameters are you actually trying to get out of this? Here's to get you started on reading that data file. You can use this for quick and dirty, just reading a text data file. You can just use the numpy load text function. Now the tags, if you do that, the tags are going to be floating points, so you can use this trick to pull out that first column and force them to be integers. For calculating the means and even the covariances, there's already a numpy function to do that for you, numpy mean and numpy code. This is a good one to know about. So go ahead, read that data file. If you don't have it, it means you haven't done a git pull since last night. So just do that now, and you'll get that data file.
So we can search this time, so you can drive.
So here's a list of the parameters that you're trying to get, and there's going to be a set of those parameters for each of the 3 tags. So I suggest that you start with the means and check that you get the right answers, because those are easier than the sigmas and the correlations.
So let's see. If I read the data.
So we're supposed to be reading the data and inferring the parameters.
Just calculate the mean of the data. Yeah.
Oh.
But you've got, it's not that hard. Yeah.
Okay. So tags. So.
Yeah, don't read too much into when I say estimate the mean. I really just mean calculate the mean of everything that's tagged with a 1. The mean of everything that's tagged with a 2, and so on, right?
So we need to select all the data values that have just the one, just for class 1.
Yeah,
Okay.
just class 1.
So for everything that has the tag equal 1, pull out the data and take the mean for each column.
Alright, so how do I do that?
And so help us with
Where you are.
and dot where or indexing. Can you index with like a tag equals 1?
Yep. So you want me to do that. The data, say, is
Can you go back to the
This one?
so where to the call. Okay. So for I'm not exactly sure how to index it, but basically for each column, take the mean of all of the values where the class equals 1.
okay. So all right. Well, let's maybe to figure out how to do it. Let's print the shape data. Alright, so it's 530 by 3, so it's 530 rows and 3 columns, right? So now what we want is to choose all of the rows where data for the first, so tags, I guess.
So if you haven't seen
Tags.
this notation before, this is a really handy way to pick out a subset of data that passes some cut, right? So this is called advanced slicing. And
So you can actually just
if they say tags equals 0, so that's going to be a whole bunch of
So you don't
trues and
even-
falses.
you actually
don't even need that.
And that will pick out just the subset of data for which that is true.
Although I'm actually not sure. Okay, so that says that there are 317 ones. So now what's next?
take the meaning
Of?
of rows along a certain. So take the mean of rows along the second axis, along the column axis.
So mean or
P dot
goes P dot mean rows and then which axis?
One, I think.
Okay.
Let's try one, and then we can just try one and then see the size.
Okay. So should I print mean rows?
Yeah.
Okay. 317?
No, do it the other way. X is equal to 0.
Three?
Yep. So we can see. We should print the. U1. Yeah. 3 1 and U2 equals 1.9. So and then we can repeat the same process for 0, 2.
So you mean for the different tags?
Yes,
Right?
just
Okay.
like everything is the same except you're
So maybe
changing.
I'll let pass the tag.
Yes.
And then
Sorry, what do you mean by pass?
so into this function, I'll say 0. Or
And then
what is it? 1, 2,
you have tags equals tag.
0.
Does anyone manage to check my numbers for the means yet?
Yes.
Yeah, they look good? Okay, these are harder. So that numpy, that covariance function, it's a little tricky because
Sigma.
when you give, so numpy arrays have a shape. So when you pass covariance an array, it will calculate a different covariance if you give it one array or if you give it the transpose of the array. And so it won't give you an error. So you have to make sure that you have the right, you put in either the array or the transpose of the array. Because it doesn't, you'll get a different answer in both cases, and only one of them is going to be right. So, and once you've got the covariance out, then you need to convert it to the more useful
So
parameters,
actually-
the sigmas and the rows.
Do you want us to do this for every tag, or should we just focus on one tag?
Yeah, well, I think you've got the basic idea here.
So we actually so. Okay, never mind. We did.
Okay, so we're going to move on. I'm going to show you the solution here. Okay, so I read the data the way I told you, pulled out the tags, and and then I just loop over the tags. So there's only, in order to get the unique tags, I just call this NT-unique, so that just give me 0, 1, 2. So I don't need to hard code what tags are in the data. And here I make a selection, tags, tag. So here I pull out data just for that cluster, calculate the mean and the covariance. And here I have to take the transpose of that. If I don't do that, it won't give me an error. It'll just give me the wrong answers. Okay, so that when you use covariance, you're taking responsibility for making sure it's giving you the answer you want. And then here, so this is a 2x2 matrix, and now I pull out the 2 sigmas and the rows. And then finally, the alpha, that's one of the parameters we have to estimate. So for that, we just take how many dots were in that cluster divided by the total number. So that gives us the alphas there. Okay, so what we just did is we solved I've invented this name because it's not really a problem people do, but we solved the tagged mixture problem, mixture model problem. Okay, so, and that's relatively easy because you knew for each data point, you were told that this data point belongs to this cluster, or this Gaussian. But now imagine, now if we just delete those very helpful tags from our data file. Okay, so effectively now we know everything is one color. Okay, so imagine now this is the data you've been handed, and you're told to fit that to 3 Gaussians. Or in the unsupervised learning context, you'd be asked to find the clusters in that data. Well, now just looking at that data, it's not at all obvious that that comes from 3 Gaussians. Okay, so that's the problem that we're going to focus on. And that's the problem that this expectation maximization technique solves. And the way it does it is it introduces this idea of latent variables. Okay, so those missing tags were so useful, they made the problem so easy that what we want to do is we want to work them back into our solution. They're not actually in the data file, but we're going to pretend as if they were. So we're going to, and when we do that, that's what we mean by latent variables. They're variables that we're going to use when in our formalism, but they aren't actually provided in the data set. And so what we're effectively doing is we're replacing the certainty of a tag. So a tag you can think of, if this is whether a particular data point, the data sample I, this tells us which of the different mixtures it belongs to. And so these are all zeros, and we just got a single 1 there. So before what we basically had, this is like what's called a one-hot encoding. Okay, it's all zeros, a vector with all zeros and just a single 1. So that's the truth about which, for a particular data point, which mixture it belongs to. Okay, we have to abandon the truth because we don't have that certainty in our data file. But what we're going to do is we're going to replace it with weights. So for each data point, we're going to keep track of what we think the probability is that it belongs to each one of those, each one of the k Gaussians. Okay, so we're going to have k numbers, their probabilities, they're all going to be greater than or equal to 0. And they are going to add up to 1 because it has to belong to one of the Gaussians. Okay, so that's kind of the cost of working with these latent variables is that you kind of take this uncertainty away and you have to now replace it with some weights. So the notation here is this is the weight that the ith data point belongs to the kth Gaussian. Okay, so and then once we've assigned these weights, if we did know these weights, if somehow you knew what the right weights were, then all you've done is we're just turning the calculation of the means and the covariances into a slightly harder problem. Okay, if you look at the documentation for numpy mean or numpy cove, it has an optional weights argument. Okay, so we would just take that weights vector, we'd take these numbers, and we'd feed it into that optional weights argument. Okay, and so effectively we'd be now using these equations. Instead of just taking the sum of the values and dividing by the total number of points, we multiply each one by its weight, and we divide by the sum of the weights. Okay, that's just the weighted generalization of the calculation of the mean, and similarly for the calculation of the covariance. And then to calculate this, to calculate the alphas, we do like that. Okay, so if we knew the weights, we'd be in just as good a shape. We just have to use slightly more complicated formulas. Okay, so that's kind of the procedure of latent variables. You pretend you had some data, and then that costs you some weights that you have to keep track of in your calculation. Okay, so just make sure that you understand what's written down here. So I want you to, there's no programming involved here. I just want you to talk about this. So tell me, what do these constants K and M represent here? Capital K, capital M. The weights in red are normalized. So what does that mean? I can write down an equation for what that means for the weights to be normalized. And then finally, I want you to sketch. So this expression down here, okay, it's a little hard to tell, but these are boldface, so these are vectors. And then there's a transpose right there. So just make a sketch, you know, with rectangles of what that expression looks like in terms of multiplying rows and column vectors together.
So I'm not entirely clear why the weights are vectors.
I think because it's so we have this file. So I think what he's saying is that we don't know the tags, and instead we're placing the tags where each row is going to get some weight that tells us the likelihood that it's a weight class.
Oh, okay. So n is the number. So n is the number of tags.
Yes.
Yeah, because n is the length of each weight, right? So n is the number of tags. K. Oh, right, because you're summing them. Alpha is the weight of something. So the little k represents which Gaussian, which individual Gaussian is that you're referring to. And then mu is the equation
so it's not the Gaussian represents what? No, the Gaussian that we have using these three parameters. What does that represent? For a given point. So these three parameters together create a Gaussian.
So alpha
what is the
is
Gaussian? Like what does it represent?
it's one of the individual. It's one of the three. So each Gaussian is one of the three. It's one of the three Gaussians that we're using to create a whole probability. We know that there are three classes. We know that we want three Gaussians.
Yeah. Okay. So then K equals what do we say? 2 3. I mean, the number of rows, which is what 530. And then what's normalized? So that means right. So if you go from 1 to K, you should get 1.
Right. So then if you just measure what equation we're looking for, then to write down the equation for normalizing weights.
Oh,
so the weights are normalized.
Okay, so let's review here. So
No,
what is
they're
capital
not.
K? What is that counting?
The number of Gaussians.
Number of Gaussians, right. What is capital M counting? The number of data points, yeah. Or yeah, it's like the number of rows in your. So if we were to think of this like a spreadsheet, so the number of rows would be capital M, and the number of columns would be capital N. That's the dimension of these vectors, boldface, x's, and u's. What's the normalization condition for the weights?
Sum over K of W I K I is 1.
Yeah, so when you sum over K, you get 1. And that you can kind of see that from this picture here. So this is the weight. Each one of these numbers is the probability that this sample belongs to mixture component K, right? And it has to belong to some component. So when you add those all up, you get 1. So you need to sum over this direction here. That's a sum over K. Okay, it's important to realize that because otherwise this expression is kind of confusing. Because is that equal to 1, right? There's 2 indices to these weights. And when you sum over I, you don't get 1. That's why this isn't a trivial expression. It's when you sum over K, then you get 1. Okay, so yeah, you need to think about that a little bit. But there's 2 indices to these weights. Are we talking about the weight for the ith data point, and also we we can say what's its how much does it contribute or belong to the case Gaussian. Okay, the last question here is sketch this expression here. So what I mean by that is, like, if I was to sketch an expression for the covariance matrix times, or any matrix times x minus mu. So that's matrix times vector. So matrix is square. Vector is a column here. So that's, and then the answer is going to be a column like that. Okay, in this case here, what we're doing, so well, another thing we could do is we could take the dot product of two vectors. So let's say b dot with b, that would look like that. And that gives you just a single number, a scalar. But what we've done here is we've moved the transpose to the right-hand side. Okay, so that's like an outer product, right? So when you put it over here, what you get out is a matrix. So in one, depending on the order of the transpose, you either go down, you change the rank of your algebraic object down by one or up by one. So but that's really important to pay attention to that, because, like, is this a scalar or a matrix? Okay, it matters where the t goes. And it better be a matrix, because at the end what we're estimating is a matrix on the left-hand side here. Okay, so what I showed you is if you knew what weights to plug in, then it's just a question of using these slightly more complicated formulas with weights in them, weighted means, weighted covariances. But we don't know what weights to put in, so we have to figure out, we have to come up with the weights first. Question?
So can you have the previous slide? So for the mu j's, why is that j different than k?
It should be k. Thank you. Yeah, I think at some point I changed. Yeah, I had a typo. I didn't have some also. Yeah, thank you. So that shows you've really dug in and understood the expression better than I did, apparently. Okay, it looks like it's okay here. Okay, so but we still need to figure out what weights we're going to plug in to these weighted mean and covariance formulas. Okay. But let's turn it around. Suppose we already knew the true means. Let's say all of our Gaussians were locked in. We knew their means and their covariances, and the alphas. We knew all of the parameters. Then we could actually calculate the weights using Bayes' rule. So what we want, the weight is just the probability that the tag for the ith data point is k. So basically, when you see that expression there, what that just means is data sample I belongs to mixture k. So we want the probability that data sample I belongs to mixture k, given it's the data point itself and all the Gaussian parameters. And we're assuming now that we know those Gaussian parameters. Okay, so we can just use a Bayes rule to calculate that. I don't want to go through all of the algebra, but in the end, you just get a nice intuitive expression. It basically just says you plug in the data point we care about. You plug it in to the Gaussian that we care about. It should be k, sorry. And then you just normalize over the probability that it could belong to any of them. So I think actually the easiest way to explain this is to go back to this picture here. So what we're going to do is for a given data point, if we knew the Gaussians, so we would basically say we look at this point here, and we say what's the probability it belongs to that Gaussian, and then compare it to the probability that it belongs to all of these Gaussians. So we kind of evaluate that Gaussian, that Gaussian, that Gaussian, and we just take the ratio of those things there. So if we knew, if the Gaussians were locked in, we could say how much each data point is likely to belong to each Gaussian. So if something in this cloud here would have a high probability to belong to this Gaussian and very low to that Gaussian. Okay, but the problem is we don't know the Gaussian parameters. Okay, we're trying to figure those out. Okay, but we now have all the ingredients, and if we put them together, the way the EM, or expectation maximization algorithm, works is that you start from some initial guess at your Gaussian parameters. Okay, it turns out it doesn't have to be a good guess, and then you repeat this cycle until you convert. You do an E step and an M step. An E step is when you estimate those weights, okay, that long stripe of probabilities belonging to each Gaussian, and you assume that you know all the Gaussian parameters. And then you turn it around And now you say, I'm assuming that I know the weight, and I'm going to estimate the Gaussian parameters. Okay, so you kind of just flip between those two perspectives. So in the E step, you're going to calculate a bunch of weights, and everything that appears on the right-hand side, you're assuming you know. You know the alphas, how strong each Gaussian is, you know where they're located, and you know their shape and size. And then you can now calculate the weights. This is what sometimes people call the responsibility of each Gaussian for each data point. And once you've done that, then you say, well, now I know this, and now I can use this on the right-hand side, and I use it to calculate the parameters of the Gaussians. Okay, so it's kind of like a trick, right? It's sort of a sleight of hand. There's two things we don't know, and we alternate between pretending we know one of them to calculate the other, and then pretending we know the other one to calculate the first one. Okay. So you can always try this, but the remarkable thing is that this works in a very general way. Okay, and it actually works. That's why I call it one of the kind of miracles of numerical analysis. This works surprisingly well. Okay, so some of the details here. So you start from an initial guess at the Gaussian parameters. Remarkably, your initial guess does not have to be close to the final answer. Okay, you can pretty much put in any random number. But you do have, the only requirement is that when you're guessing what the Gaussians are, you have to make sure that you can't just say they're all the same Gaussian. They have to be distinguishable, otherwise things are going to blow up very quickly. In practice, if you're worried about efficiency, then rather than just take a random guess, what's used is the k-means algorithm, which you heard about earlier, is used as a starting point for this. And in fact, k-means is a special case of a Gaussian mixture model. So it is actually kind of a subset. It's a simpler problem than the general Gaussian mixture model. But it goes much faster, so it's appropriate to use as an initialization for the Gaussian mixture. So that's one thing, is you need to figure out your initial guess. And then the other technicality here is when I say repeat until converge, well, what do we mean by that? So what we care about is basically the goodness of fit. And we'll monitor that using the log likelihood of the mixture model. So it's written like this. So we're just taking this is our probability. We'll take the log of each one, and we sum that over all of the data points. Okay, and the remarkable thing, the miracle of the EM method, is that if you just alternate between the E steps and M steps, every time you do one cycle of E and M, this log likelihood always gets better. It never gets worse. Okay, so you're guaranteed, you may not get better by much, but you're guaranteed that every pair of steps, E, M, you're always going to get closer to a minimum. So pragmatically, what you do is you just monitor the fractional change of this log likelihood, and once the changes are small enough, then you say that you're done. Okay, so how do we actually do this in practice? So rather than have you actually write, I mean, you could code up the equations that I put right there, but in practice, there's a bit more details to it. For example, like doing that k-means initialization. Yeah.
When you talk about the tolerance level, like how small is small?
How small is? You have to. I mean, there's a default in scikit-learn, which I'm talking about now. But I found actually that you need to for your problem, you need to try changing different values and decide what a sensible convergence is. Yeah, there's not really a good absolute criteria, I think, for setting that. So. Okay, so rather than have you code up those formulas that I put there, so now I want us to jump and actually use what most people use for this, which is the sklearn has this mixture module, and it's very simple to use. You just sklearn mixture, Gaussian mixture, you just tell it how many Gaussians you want to look for. And then you tell it to fit your data. So this is using exactly the same pattern as all of the sklearn stuff that we heard about before. They all have a fit method, and they often have a sample method as well. And then after you've done the fit, then you get the answers out. These are the alphas. For some reason, they put underscores at the name of all of their class attributes. Mean underscore covariance is underscore. That underscore shouldn't be there. Okay, so what I want you to do is the same data set you already loaded. I want you to fit it using sklearn. Okay, but now you're not allowed to use the tags. Okay, so we're going to fit the same data set, but I want you to throw away the tags. So this is how you do that. You just just take a slice that ignores the first column, which had the truth tags in it. Just kind of putting these two together.
I think your turn too.
Are you driving or am I driving?
I am just trying to make us to work. So you are typing. Oh, okay, yeah, no. And then I would just make a variable end up because then if you want to change it, maybe make a variable just in there.
So if you should, okay, I'm sure.
Yeah, and then it's
It's tagged, right? It's mystery.
oh, you said to do the thing.
Exactly. So with that.
Right, so you just pick the two. So that's why you have the one colon. That means pick the columns beside the one.
So you're looking below this?
Yep, data equals everything. So you're using your choice.
I don't think it's underscore before.
No, you're right. Yeah, I said that. Sorry. Yeah, so Eve just reminded me, so that there is no, that's a typo, there's no underscore right there, so. So you should get, these are the answers that I get. Can anyone verify any of these? So this is using sklearn. So when I call it untagged because we're not using that first column.
Yeah.
What do you agree with everything there?
Well, I agree with the order of the tags.
0, 1, 2.
Yes, but everything else is right.
Sorry, do you go to the previous slide, please?
Yeah.
So is the order of these two boxes right?
I think he's showing how
Yeah, no,
you
you're
use it in
coding
general
you'll
on top.
have this first,
But
and this will be inside.
yeah.
Okay.
Okay, I see.
Yeah. You do tasks. It's a trick, like, try to
think that was 3 dimensional.
Am I right?
Instead of 2 dimensional. So it thinks that the 1, 0.
Okay, so let's look at the numbers that I have up here, which I think several of you have already got. So here I put the truth. Okay, so that's what I use to generate the data that you're reading. This is what I refer to as a toy Monte Carlo sample this morning. It's where I know the model, so I know that it's the right model. So I don't have to worry about model comparison. Here's what we got when we use the tags. So we're cheating and using the truth. And here's where we solve the much harder problem it requires introducing those latent variables using the untag, but in practice it's very easy because sklearn does all this work for us. So let's just look 0.1, 0.102, 0.102, 0.6, 0.598, 0.3. What's going on there?
They're sort of mixed.
Yeah, they're mixed. So I mean, scikit-learn doesn't have any notion of how we numbered them originally, right? So it's just going to the order in which they come out is going to be random. Okay, so in fact we need to match this one with this one here, but still that one's only off by 0.002, and this one's off by 0.03. Okay. So what you can see is that you get the errors are larger here, right? We're not able to measure those Gaussians quite as well because we don't know the color of each dot now. Okay, there is in the overlap regions there is some uncertainty. Okay, so inevitably that feeds into an uncertainty in the Gaussian parameters. Okay, and I'm not showing errors here, but they have larger errors, and we should expect that. Okay, so an important point that I've just swept under the rug so far is so when you initialize the sklearn thing here, when you make this object, you have to tell it how many Gaussians you're looking for. Okay, so what number should you give it? Okay, and so this is an example of what I referred to this morning as a hyperparameter. The number of Gaussians is a hyperparameter of the EM algorithm. Okay, either you just have to know what the answer is going to be, so effectively you're just going to set it a priori, or you have to somehow estimate it from the data. So most often what people do is they're just pragmatic and they use this Bayesian information criterion, BIC, that we heard about earlier today, in order to pick the so-called best value of k. Because there's other ones, there's the AIC, the DIC, and you come up with your own IC, and they're all going to give you similar answers. Okay, but this is like for quick and dirty work, you just want to figure out should this be 2 Gaussians or 10 Gaussians. That's fine to use the BIC. If you want to be more rigorous and Bayesian about this, then what you need to do is you need to consider a range of values of k. Okay, so probably let's say from 1 to 20. Why not 21? Okay, well that's you have to just because you can't go up to infinity, so you're going to have to pick some range. And now you need to treat this as a model evaluation problem. So you need to do your whole problem, your whole analysis for each of those different models. Each hypothesis about the number of Gaussians is a different model. And you're going to need to calculate the Bayesian posterior of that model, and you'll need to use that to weight any answers you get. Okay, so it's a pretty complicated process, which is why people often don't bother and just use something like the BIC to do model selection. Okay, but in a strict Bayesian model, you can't select a model as a Bayesian process. So we heard yesterday the sklearn also provides this thing called the Bayesian Gaussian mixture. I actually don't like that because it actually has more hyperparameters. So it's not. I don't find it's actually an obvious improvement over BIC. It gives you this sort of this false sense of confidence that now you're being a card-carrying Bayesian. So really, if you want to do things right, you have to bite the bullet and think of this of a model averaging problem. You're going to have to study multiple models simultaneously and average over them. Okay, so what I want you to do is I want you to just quickly the code you just wrote. I want you to try fitting with different numbers of Gaussians. Okay, in this case, we know the answer is 3. That's the true value. But I want just to get a sense of how much how useful this BIC is. I want you to just look at see how the number changes when you have 1, 2, 4, 5. And how do you get the BIC? It's very simple. Once you've done the fit, you just say model.bic. It doesn't remember the data, so you need to give it the data back again, which means that you could now calculate the Bayesian information criterion for a different data set if you wanted. And you don't need to make a plot. I'm going to show you a plot. Just look at the numbers, how they compare.
this is just.
Yeah, I'm not worried if you don't understand this. This is going to complete the situation. Would you mind going back to the, or I guess thank you.
The answer for the last one. Yes, thank you.
So is BIC a single numerical value? It's supposed to be single numerical value?
Yes.
So it's supposed to be a large numerical value?
It really depends on your data. So.
What?
I think there might be something wrong with our last one. Would you mind coming to take a look?
Yeah.
So when we
Yeah, I'm
Also, there are 4.
It was 0 and next.
Type for the.
oh wait. No, here. It is.
Oh, are they mentioning it?
There's the 4 point. Or no.
Yeah, you have the same numbers.
Model weights. Model means.
You have them in a different order.
Oh, but then, so these two. Oh, I think I wasn't understanding. Could you, when you do a print, could you print like weights, string, colon, that, and then means string, colon, that?
Okay, so Anna and Lee noticed an interesting thing. So when they ran this, they did not get the same order. Okay, we already talked about why this order doesn't match this one, but how come 2 people running sklearn get different orders? Okay, so the reason for that is that the way that this thing is initialized is using the k-means, and the k-means actually has a random seed. There's a random element to it. Okay, and also by default, I think when you use sklearn for the Gaussian mixture, it repeats from multiple random starting points. Okay, so there is a random element to this, and so you end up getting the same numerical answers, but the order can actually be different. So don't panic if you see that.
There are 12.
Okay, so this is these are the numbers that I get. So you're asking me if it's a big number. So it's hard to really say what context for what's a big or small number. It really depends on how good your fit is and what the data looks like. So really all that matters is not the absolute value, it's the changes. Okay, so what we see is that 3 was the BIC agrees that 3 is the best answer. When you increase the number of components, it gets worse, but only slowly. If you decrease the number of components, it gets worse pretty badly. And that's kind of, if you look at the original data, you can see why 2 or 1 would be a really bad. This is a lot of points that wouldn't fit. So it's interesting to dig a little deeper. Instead of just thinking of the BIC as a black box, but actually look, what is BIC calculating? And what it does is it has 2 terms that get added together. There's this one here, -2 log likelihood, and that's basically the goodness of fit. With this -2 log factor, that's basically like chi-squared. And then this term here is measuring the naturalness of the fit. So it's just like when we talked about Bayesian model comparison earlier. I talked about how a more complex model just inherently has a penalty in it, and so this BIC is trying to capture that with this second term. If you have 2 models that give you exactly the same goodness of fit, this term will be the same, but the one that has more parameters is going to get penalized by this term. Okay, so and what is this term? It's the number of parameters times log of m, so that's the number of samples. Okay. And the number of parameters here is large, okay, because each Gaussian has a whole bunch of parameters, especially in a large number of dimensions. If you actually calculate right out what the number of parameters is, this is what you get. These ones for alpha, mu, and then c. So most of them are here because it's a matrix. So this one blows up pretty quickly. So the BIC has some Bayesian elements in it. If you click on this link here, details, there's actually a nice, these are someone's lecture notes, where they go through and show in what limit the BIC is actually a rigorous Bayesian calculation. Almost never in practice, but you're often close enough that it's not a crazy thing. So to do. So that's why of that whole alphabet soup, AIC, BIC, that's why I usually prefer BIC. But if you're going to go that route, just remember this is kind of an ad hoc thing, and it's not really the rigorous way to go. Okay, so last exercise here. So now I've given you a different data set in the same directory that's called mystery.dat. Okay, so all you need to do is just change. This one doesn't have the column, the tag column in the beginning. Okay, so you don't need to slice away that zeroth column. And I want you to tell me how many Gaussians I should use to fit this data set. Okay, this is only one-dimensional data. It's just one column of numbers. Okay, so don't think of this as a scatter plot. Think of this like a histogram. So it's different data, but now it's one-dimensional. But you don't need to tell sklearn the dimension. It just figures it out from the shape of the array that you pass.
What's the BIC again? How do you call BIC?
It's model.bic, and then pass it the data again.
Okay. So, what do you want first?
So let's do with or I guess we could even just pass if you took the name of the file as the just yeah, so you took the name of the file and asked the number of Gaussians.
Do you mean just evaluate it for a random Gaussian?
Yeah, let's just try 3. Oh, because now we don't want to do the column anymore. Sorry, I wrote that first. I guess just comment that out for the Oh, there's only one column.
Has anyone made a histogram of this data yet?
It's like a 1D Gaussian.
Sort of.
Is it, it's only, the data set is supposed to be only one column.
Yes, correct. Yeah, it's one-dimensional.
Oh, I see. So that means the problem is
Like
that.
a normal distribution or here Gaussian. Yeah.
So how many Gaussians do we want for this? If we just blindly follow BIC?
1.
1, 8?
With 8.
8?
BIC.
Anyone agree with that?
Oh, so somehow our array is up for I think it's just in the estimate tag. Because we
My first
data there.
Basically, it's when you read that non-dimensional array. So,
Small number there.
What if you try with the like 1,000? Gaussian.
negative 1 comes
Would it be better?
Oh, and you know,
reason why this would be really slow.
No.
Yeah, yeah.
Especially if you like using
And gals.
Yeah.
So what, just back up for a second, how are we supposed to check which value of BIC we should go run? Because I think we missed that last part.
Oh, no, I guess the way I don't know if it works.
But I wasn't even sure how to like just iterate over a couple of Gaussian.
Yeah, to try this one.
Okay.
I think what you're saying is that the answer should be, yeah, it's just like one. Oh, I just.
It looks like you could only use one.
Yeah, I think we should find that that's
Well, it's also one-dimensional data.
Yeah. So it's that somehow there should be, all the data makes one Gaussian, but you could also imagine a situation where you have two Gaussians. So I think that's what we're trying to figure out. I think that's the I'm confused about, I don't understand why.
File, that's fine. The errors coming in model fit.
Yeah, right?
Try it out. Yeah. Look at the shape, so.
Okay, so here's the code that I use to do this. So I load the data. So actually, I'm not sure if this is important or not. But so normally, whenever you pass your data into scikit-learn functions, it wants it to have like two dimensions. So in our case, since it's one-dimensional, what I did is I did this little trick, reshape. So this is basically going to add kind of a dummy dimension. So it'll take something that's one-dimensional and make it like a matrix, but where it's just n by 1. And so that might be the problem that you were having. Let me actually just try and see what happens if I leave that out. So it does seem to make a difference. It shouldn't take that long. Okay, so I think that is actually important then.
So
Okay, so I should have warned you about that. You do need to have that in there.
Oh, I see what you mean.
Okay, so see how much faster it was when I put that reshape in there?
Yeah, fixed it.
Yeah, so I don't know why it doesn't complain. Why I mean, it should just say that it doesn't have the right number of dimensions and complain straight away.
Oh wait, do I take out?
Okay, so this is the plot of the BIC versus the number of components. Notice that there's like an extra 0 here, so don't worry about the absolute scale of these things. It's just a relative change that matters. So there's a very shallow minimum around 8, say, and it has the same general trend. The poor complexity kind of picks up slowly, and the penalty for poor underfitting shoots up more rapidly. The same trend we saw before. If we actually look at the best fit, so this is what the 8 Gaussians, I actually plot them. They did a pretty good job of fitting them, right? But does that seem like a natural fit?
No.
Right. The idea of the Bayesian model comparison is we're supposed to pick the one that's most natural. This rise is supposed to penalize unnatural fits. Okay, but as I think you guys pointed out, so this looks kind of like a Gaussian, right? There is actually, I generated this data with just one Gaussian, but I truncated the Gaussian. Okay, so there is really the natural model you would hope to be able to discover if you were trying to learn this data would be that it's a single Gaussian that has been truncated. So it has the parameters would just be the mean, sigma, and where you truncate at. Okay, but we didn't even consider that in our model space. Okay, so that's kind of an example of a gotcha where it's always really important to look at your data and to do these kind of basic sanity checks and not just blindly. We have a nice minimum here, but this is really not what you want as the most natural model. And this actually came up in a problem that Bella was working on, where she was using a Gaussian mixture model to simulate targets, tracers, for the DESI survey. So we basically have all this imaging data, different types of galaxies, and she wanted to simulate new data in the multidimensional space of like R band magnitude, Y magnitude, things like that. And the reason we had this sharp edge in there is because there were cuts, right? We made cuts on the magnitude. So we had nice, simple distributions, multidimensional Gaussians, but then the cut made it so that the Gaussian mixture model really went crazy, and it wanted to make all of these small components to try and fit this thing. Okay, so this is kind of a cautionary tale that although it gives you an answer, it's not really the right answer. Okay, so what are the use cases for Gaussian mixture models? So first is in the machine learning kind of orientation, then it's a go-to method for doing unsupervised clustering in the data. Although it's not totally unsupervised because you have this hyperparameter, which is the number of clusters of Gaussian that you're looking for. And also, if you're using this for clusters, normally we think of clusters as visually separated, but in the Gaussian mixture model, there's nothing that requires them to be separated. Okay, they can be quite overlapping, and if that's the best fit, that's what it will give you. So, another thing you can do is to basically create an empirical sampler to simulate data. So that's what Bella was doing. She had a whole bunch of imaging data. Basically, had a catalog, and we wanted to simulate data which looked like it came from that catalog. So we just took the fits table, fed it into the sklearn mixture model, and then used this sample method. So once you fit to the data, you can just ask it to generate samples, and you tell it how many galaxies do you want to simulate, and they will look as if they were sampled from the same multidimensional distribution, under the assumption that the distribution is well described by a sum of Gaussians. You can also use it to perform maximum likelihood fits to mixture of Gaussian. Okay, this is really the only way to do this with a large number of Gaussians. If you do this to brute force and use like a optimized gradient descent, that'll never work. And then coming back kind of the Bayesian perspective, so the right way to do all of this stuff is with probably a Markov chain Monte Carlo, that we'll talk about tomorrow. But these good classical Gaussian mixture models are still essential there because you need to start your Markov chain Monte Carlo from a good starting point. Markov chain Monte Carlos are terrible at optimizing, finding good starting points. And so what you want to do is you want to basically bootstrap it by starting from a really good starting point that you get from a mixture model, and then feeding that into using that to seed your Markov chain. Okay, so just to last exercise, this is just something I want you to discuss. So this is a problem that I've been working on recently, and that is how can mixture models help to detect and measure faint galaxies in an image? Okay, so here's an image, a little cutout from an LSST image, and there's two sort of a blobby, sort of Gaussian-ish objects. So how can you use what we've talked about in this lecture to find and measure the properties of those galaxies? So in particular, let's say we've got some function load image, and so it's going to give you an array, a two-dimensional array, which tells you the number of photons detected in each pixel. So how would you take that information, the number of photons per pixel, and turn it into some data that then you could feed into a Gaussian mixture model fit?
1D array with the number of entries being the number of pixels.
Okay, so that's so we're saying if there's a 20 by 20, so we'd have 400 400 dimensional space.
Yeah.
So what that would really be doing, in that case you'd only have one data point. Or do you mean 400 data points for each pixel?
I guess 400 plus. Is there a difference? 400 data points.
It's a little tricky, yeah. So now, but 400 data points, you somehow you have to encode the information that these two pixels are close to each other, and these ones aren't. But normally when we assume that there's no ordering to the data. So I really want this to work because this is one of these numerical miracles. I want to be able to apply this to LSST data, but it's not obvious. Do you have an idea?
If the pixel has 100 photons, you add in 100 data points at that point.
Yeah, so that's what you could do. And so what we're realizing though is that the Gaussian mixture model fundamentally assumes that your data is unbinned, right? So if your data consists of photons, then it wants to know about every single photon. Okay? So what we can do is we can kind of reconstitute the photons by saying, okay, that pixel has say 10 photons, so I'm just going to give it 10 photons. Now I need to tell it where those photons are, right? So I'm going to end up with 2 columns of data, basically X and Y, and I'm just going to I can either put all of my photons at the middle of the pixel, or I could say they're randomly distributed in the pixel, so I just generate random numbers and give them all coordinates, right? So basically I'm going to have my data set, the number of rows is going to be the total number of photons in this image. Okay? And then the number of columns, this is going to be 2, because each photon is just going to have 2 numbers associated with it, an X and a Y, and it's going to be within its pixel, and then either I'll just lock it in the middle or I'll do that. So that works. It turns out it's not the optimal way to do this. So what I've been working on is a way to do this better. So I'll come back to that at the end. So just give you some practical advice about how to use this stuff. So the expectation maximization always converges to a local maximum. So that's great. Every step, every pair of n steps you take always moves you closer. But you're going to a local maximum, and you have no guarantee that it is the global maximum. And so that's why sklearn retries. The algorithm is so fast that it just retries 20 times and then remembers the best maximum that it's found so far. So the advice here is to repeat with different random initial parameters. By default, sklearn already does that for you. The Gaussian mixture model does not perform well under certain conditions. One of those is if you have a flat, non-zero background. And that's actually the case here, right? So we have some sky here. We have some sky here. It's very hard to model that flat background with a Gaussian. You can imagine a Gaussian that's so wide, that it basically is it extends and covers this whole region. But then you run into this problem here, that it's be truncated by the edges. You run into this problem, right? So your sky would be truncated, that wide Gaussian would be truncated the edges, and so it would end up using lots of small Gaussians to try and accommodate it. So if you have, it really requires that the data, that you have blank space between your clusters. Okay, that's another assumption. That your data is unbinned, and that most of the space is empty, and then you have localized clusters. So you can't have outliers, you can't have any flat background. We already saw the problem if any of the components is truncated at a boundary, so like at the edge of an image, for example, or a spectrum, that's going to cause problems. And then the last piece of advice is you need to consider your choice of k carefully. And there's really no one right answer. Sometimes, like in the application that Bella was doing, all we needed is we just needed some model that was good enough. We weren't trying to learn anything about galaxy evolution from the Gaussians that it ended up with. We just wanted it to do a good job of mimicking the observation and to be able to generate new samples that looked close enough to the observation. So don't, in that case there it's fine to use BIC or even just to say I'm going to just work with 10 Gaussians. But then sometimes you really need a full-blown Bayesian approach, so you should be aware of what that entails. It is doable, but it's a lot more work. Okay, then, so we focused on Gaussian mixture models as the application of EM. But it's actually the reason this is such a powerful technique is it can actually solve a much broader class of problems. So basically, any mixture that you have can be solved with the EM algorithm. If you look at the proof, it all boils down to this rather simple geometric picture here. It depends on this thing called Jensen's inequality, which in one dimension is just saying that when you draw a line between any 2 points on a parabola, it's always going to be above the parabola. Okay? So it's a statement, and so the parabola now becomes generalized to a convex function in n dimensions. And what it says is that if you evaluate any function, any convex function on the expectation, so you put the expectation inside the function, then that's always going to be less or equal to the expectation of the function. Okay, so we're just kind of changing the order of taking the expectation value and taking the function. Okay, so that's a very general statement, because x is drawn from any probability distribution, and f it can be any number of dimensions, and f is any convex function. Okay, so it's a very general thing, and that's what the general expectation maximization algorithm relies on. That's what guarantees that your log likelihood always gets better with each step. So the kind of full class of problems that you can solve is you've got any PDF, any probability density function that you can write as a sum. So kind of the first thing in the expression has to be a sum, and that's the only restriction we make. The parameters theta can be anything. And the latent variable can be arbitrary. So whenever you think, oh, it would be really nice if I just measured this thing here, and that would tell me which one of these different probability density functions to use, then you should think about how to turn this into an EM problem. It turns out that the E step is essentially unchanged, and you can do it in a closed form. The M step becomes, though, a lot more expensive. So I'm not going to go through the details here, but I've just written here for your reference. So the E step and the M step in the most general case look like that. The formulas actually look a lot simpler, but that's because there's basically a lot hidden in them here. To go from here to here, we use Bayes' rule. Okay, but this is a much more useful formula because we just have to evaluate Gaussian. So you've already wrote code to do that. Over here, there's a very lengthy calculation in the Gaussian case to show that this is actually the correct maximum likelihood solution for the solve the weighted covariances and mean problem. But in general, you have this pesky argmax here. So that's mathematician's notation for you've got to call something inside the optimized. Okay, you're going to have to do some nonlinear iteration. So there's only very special things that you take mixtures of. So basically things in the exponential family, not just Gaussian. Anything that's e to the something where you can there's going to be a closed form solution. But even still, this can still be a very useful approach. Even if you have to do some iteration, it's going to be slower, but you're still going to have the very robust numerical convergence properties. Okay, so then just the last two slides. So these are just examples of kind of more advanced techniques, so where people have leveraged this really powerful EM approach to solve kind of seemingly very unrelated problems. So this one here is from one of my collaborators on DESI, Stephen Bailey. So he has used the EM, iterative EM approach to solve the PCA problem, so solving simultaneously for the principal vectors and the principal components of data that's weighted. Okay, so remember I said it's really, whenever you're looking at an algorithm, you should always ask the question, well, does it handle weights, or can I tell it the errors on my data? And so this is a generalization. If you look up the textbook PCA, it doesn't know anything about weight, so it just assumes that each observation is equally valuable. So this is a generalization that uses the EM technique and allows you to provide weights as well. And like the extreme case of a weight being infinite means that, or zero, I should guess, means that the data is missing, right? It has such a big error that it's basically the data is missing. So here's some data, and you can see there's just some parts of it are just being deleted, and it's also the data's got some noise. And then using this technique, you can actually recover a nice noise-free signal, and you don't have any problem with the missing data. So that's an example of something that seems to have nothing to do with Gaussian mixture models and expectation maximization, but that Stephen figured out how to kind of transform the problem and to take advantage of that powerful numerical technique. And then this is coming back to what I was talking about before, this what I've been working on to try and use the EM algorithm to generalize it to work with data where you don't know where the individual pixels are, or the photons are, you just know how many are in a pixel. So there's two issues. One is you have to be able to handle a flat background component, so that's a non-Gaussian component. That's pretty straightforward. And then the harder thing is the bin photon. And the trick is that you just need to add more latent variables. Okay, in addition to the ones we talked about, you add one extra latent variable for every photon in the image, which tells you where in its pixel it was. Okay. So it's actually that's two coordinates. So you add an x and y for every photon that tells you where in the pixel it was. You don't measure that, but you'd like to know that. Okay, so that's when you want to use latent variables. You say, well, I'd like to know that because that would make the problem a lot easier. And you do that, and it turns out that you can you now have a kind of a more complicated EM problem, but you can properly solve for that and you end up with an algorithm which is very fast and accurate. So it does a lot better than just kind of randomly putting the photons in here, because it uses the information about the shape of the Gaussian to figure out where the photons are most likely to be in the pixel, and also handles edge effect and things like that. So this is a GitHub repo where I'm working on that. So just to give you an examples of kind of, you should think of the EM technique not just for what it does with Gaussian mixtures, but as a kind of a building block like fast Fourier transforms. That's really powerful, and you should always look for opportunities to kind of leverage these very powerful fundamental methods. Okay, so it's been a long day, so thank you.
All right, thank you, David. Before we break, are there any questions?
So how would you handle truncated Gaussians? Like, is there a version that fits Gaussian with the truncation parameter?
So this does here actually. So one of the things you get for free with the binning is it has no problem with the Gaussian that's truncated. So the answer to your question, if your data isn't binned, then you'd actually need to bin it in order to take advantage of that.
Would it be better to not use the sourcing profiles, or does it not make much of a difference?
Okay, well, yeah, that's a good question. So, so galaxies are not Gaussian, so obviously you know something about galaxies. But it turns out that, well, first of all, you can approximate quite well as like a search set n equals 1, n equals 4 with about 10 Gaussians. Okay, so it means you're going to have a more complicated mixture, but there's actually no problem representing the search set, just converting them into a sum of Gaussians. But it turns out what's special about LSST is that most of our galaxies are going to be pretty crummy, like this, very low signal to noise. So although this may be like some complicated morphology, when you look at it with such a low signal to noise, then just a few Gaussians is going to capture basically all the information that's really there in the image. So, yeah. And LSST has the other problem that we need to measure the shapes of billions of galaxies, so that the amount of CPU time that we can spend on each little postage stamp like this is really tight. So anything that can work quickly is going to be essential. So.
All right, if there's no further questions, let's thank David one more time. It's about 5 after. Our dinner reservation's at 7, and Lucianne is going to lead